Okay, let's continue to another video sections of this point cloud video series. In these video sections, we will discuss about this canonical capsule. I think this is an important works that address the important property in the point cloud understanding, which is rotation invariance. And this is the list of the three issues that are associated with this point net, as we discussed in the previous video sections. And in particular, this canonical capsule addressed this second issue, which is simple alignment associated with this point net. That is, it's still relatively sensitive to affine transformations. Again, if we have a neural network here, if we have this input point cloud, and if we rotate this, the performance of this neural network after we do affine transformations like rotation or translations, let's say the segmentation output will be dropped to some degree because of this. It's not really sensitive to affine transformations. Okay, so let's start talking about the motivations of these canonical pose first. Most of the 3D model datasets, such as ShapeNet dataset, are object-centric. So we have the object, the clean object without the backgrounds. And also, those objects are pre-canonicalized. For the formal definitions, you can search your own on the internet. But in this case, I want to simplify these definitions specifically into our use case, which is this point cloud understanding. And I itemize in these three important properties. The first is the orientations are well aligned. For example, if we have several same object like airplane, the airplane cockpit is always along with this x positive directions. All are aligned, but the pose or these directions can be any directions. It's just a conventions. So no matter the pose, as long as all the objects are consistent, it is okay. We can say that those are well aligned. And then the second item here, they are scaled into unit into same scale. For example, we use a unit spare here. This is a positive 1, this is minus 1. Positive 1, this is minus 1. And then the third item is they have the uniform origin, which is the zero center. The origin is 0, 0. Yeah, this is the properties of the most common 3D model dataset that we have right now. And a lot of differentiable 3D encoders, for example, PointNet++, and other encoder, they are heavily affected by this pre-canonicalizations. Let's say if we have a dataset that are not well aligned, we have several pose here, like this pose, and then we have another pose, and we use the same pre-trained model neural networks that are trained using this well-aligned dataset. We will encounter a performance drop. Let's say if we test using well-aligned dataset, we have 90 something. It can drop much lower, for example, like 70 something or 80 something. Yeah, you got the idea. The performance will be dropped because of this affine transformations. They are not really sensitive of this affine transformation. So let's start discuss the high level idea how this method address this transformation invariance. So this paper introduced a canonical capsule. Canonical we already discussed with these three properties here in our point cloud understanding context. And then capsule in this case is this correspond to its decomposed region. We can see the same color here correspond to the same capsule, or we can say just cluster. And then this paper tried to decompose into K capsule, where every pose is correspond to the the centroid, the center of the capsule. The poles are transformation equivariants, and then the capsule descriptor are transformation invariants. I will discuss later. We will discuss later in the detail what is this and also why they are important. So after this, we learn this encoder that achieve these two property. In this way, later, a pair of point cloud sample, we can canonicalize them into a same pose, which is a convention across all the object. For example, we have this kind of original pose and this pose, and this is the convention of the canonical pose. Yeah, this is the high level idea, and we will discuss the more details in the next few slides. I hope this makes sense to you. And let's discuss the first property, which is transformation equivariance. So let's say we have the point cloud P here, and then we have the encoder or just any function. Q is the output after we apply this point cloud into this encoder function here. And then we have another point cloud, but we transform this point cloud. For example, we rotate and also we translate with this kind of pose here. And then this is the Q prime, is the corresponding output of this transformer P, which is P prime. And transformation equivariance means we can transform in the input, and in the output, we apply the same transformations. These two are equals. You can try to see this diagram. And then for the formal definitions, I hope this can provide easier understanding after we see this formal definition. So applying a transformation to the input and then applying to the function equals to applying the function first and then the transformations to the output. See this mathematical formula here. This is the same input P here, and this is we apply the transformation first, and then later we apply the functions, equals to we apply the function first, and then we apply later the transformation. So we swap this order, it will be the same. This is the transformation equivariance. If this function or later point cloud encoder hold this property, it means that this function or this encoder hold this transformation equivariance property. That's it for the first property. And then the second property is transformation invariance. We have the same point cloud. This is the encoder or just any function. And then this is the corresponding output. We have another P prime, which is we apply a transformation to this P. And this is Q prime is the corresponding output. So the output will be the same because they are transformation invariant. So no matter the transformation we apply in the input, the output are just the same, invariant to any transformations. And yeah, this is the mathematical formula. No matter we apply any transformations, the output after we apply the function will be the same. And let's see in the context of this canonical capsule. Let's review them, these two properties. So this transformation equivariance is associated with the pose, this one, the centroid. It means that if we apply a transformation in the input, we have this is the original airplane. Sorry, the drawing is quite bad. If we transform into TA and we have this is a T transformation P here, we transform into this. We transform into this. We can rotate this to be aligned into this in the input space. We can also do this the same transformation TA and TP after we pass to this encoder here, which is in this case is the pose, this capsule centroid here. We also can use the transformation to rotate using this TA and TP, and we can align these two. So these two alignment can be done before we apply this function extractor or after we apply this extractor. It means that this extractor are transformation equivariants. And then for the capsule descriptor, we associate with this transformation invariant. It means that no matter the pose, for example, if we have this capsule that is associated with the head of airplane, no matter the pose of this head, we should have the same descriptor, like this and this. Their descriptor, which is the features embedding, should be the same, no matter the pose of this airplane. So this is the review of the two properties in this canonical capsules paper. Okay, so let's discuss about the end-to-end pipeline of this method. We have this number of points, and in their paper they visualize by using a 2D to simplify the visualizations. But actually in the point cloud we have XYZ, but I think it's fine. It's just visualization to make easier understanding. Okay, so we have this number of input point, and this is the XY. We apply a transformations TA and TP here. After applying transformations, we have this kind of pose, and we have another pose like this. You can see here. And then we extract a point features. This is the same number of points. And then we have another embedding dimensions. We can use a point net or other point cloud encoder to get this point features. And then next we will extract attention metric. The row is the number of capsule, which is in this case is K. K is 10 here, 10 capsule. And this is another dimension. The column is the number of points. So it captures the relations which points belongs to which capsule. Basically, this is just attention metric. And then using this attention metric, we compute the capsule coordinate, which is the capsule pose here. In this page, I will give the high-level introduction first. Probably you do not really get the detail, so we will jump into the details in the next few slides. So I just want to explain the end-to-end pipeline in high level. Okay, so let's go back. This theta K here is the centroid of the capsule, like this capsule, this capsule, this capsule, and so on and so forth. We have the 10 capsule, and this is the coordinate. In this case is XY. For 2D or 3D will be XYZ. And then the beta here is the corresponding descriptor. So this is the centroid, and this is the descriptor. We will have the same in the lower transformation TP here. And then next we want to estimate a canonical pose, which is the theta bar here. A canonical pose can be any pose, but all the objects must agree to have that pose. For example, this network agree that all airplanes have this kind of pose. And to estimate this pose, we will use this descriptor, apply to this K here is MLP, to estimate a new pose that is a canonical pose, that all the object must agree to this pose. Okay, so after we have this pose, we will align this pose from the transformation A. In this case is this kind of pose. We want to rotate this, right? Rotate this like these directions to have this kind of directions by applying a shape matching. Again, we will discuss later. After we apply this shape alignment, we will get this transformations, which consists of rotations and also translation. Okay, and in this case, this is the canonical pose. We will concatenate with the descriptor. This one, we have the 128 for the descriptor, and also the centroid here. We only have 2 embedding dimension. So if we concatenate these 2, we will have the 130. So we concatenate this as input to a decoder, and this decoder we will reconstruct this. This is in the feature embedding. We reconstruct into the original shape here. And in this case, we reconstruct from the canonicalized pose. In the feature space here, we already aligned into a canonical pose. So we expect that the reconstructed shape will be also in the canonical pose, right? And then we have these transformations that align this centroid here in the space. We can also use this same transformations to align this original input here before we apply to the encoder. Okay, so the PA here correspond to this PA. We apply this transformation to rotate this kind of pose into this pose, and yeah, we can just equalize these two and compute the chamfer distance, the reconstruction loss. Yeah, so this is the end-to-end pipeline, and don't worry, we will discuss the more detail later one by one. Okay, let's start with discussing the encoder. So in this encoder, we have the shared the same encoder here to compute the branch, the upper branch, and also the lower branch here. And the encoder basically just consists of this point-net-like encoder from this number of points and with xy here, or xyz in the point cloud. Again, this is just 2D for visualizations. We map into this embedding dimension of C here, 128 here, point features. And then next, we will compute the attention metric. In this paper, they use a convolutions, or we can basically use MLP to map this 128 into 10. So after we do this mapping, we will have this 1024 by 10. And basically, we just transpose to get this shape. And we will use this as attention metric to capture the relation between points to the capsule, which point belongs to the every capsule here, every cluster. Okay, that is for the encoder, and let's go to the next component. In this case, is the capsule pose. Capsule pose correspond to this one. We have the number of capsule, and we have the number of centroid, and how we compute this centroid for every capsule. So we have the attention here. Attention we compute from the previous slide here, this attention. Okay, we have this attention, and we have the corresponding point here, and this is the dimension. The attention is 10 by 1024. 10 is the number of capsule, and the point is the number of point here, and this is the coordinate x and y. We do the dot product metric multiplications, and we have this 10 by 2. So we have the 10 capsule, and it consists of the coordinate. So we have the 10 centroid. And then for this attention metric, we do some normalizations. First, we do the column-wise normalization. It means that for every column here, we normalize. We can use a softmax normalization here. It means that we want to encourage for every point here belongs to which capsule. We have the 10 capsule, right? And we have 1024 point. For every point, we ask each of them to attend into certain capsule. This is why we have the first normalization column-wise. And then the second normalization, which is row-wise, we want that every row here, the total attention sum to 1. It means that the contributions of every row here among all the rows are the same. That is the meaning of this second normalization. So let's more dive into this. What's the meaning of this? Again, this is the attention metric. Attention metric will capture the relations, which point belongs to which capsule. Let's say for this capsule, here, those point belongs to the first capsule. Let's say this point, this point, this point, this point, this point. So this all points that attend to the first capsule, they have higher attention. And if we multiply this to this, it means that the coordinate here of the first capsule are highly impacted by those points that attend to the first capsule. This is for the x coordinate. Likewise also for the y coordinate, which is this multiplied by this. I hope it makes sense to you. Yeah, so again, yeah, this is how we can compute the pose, which is the centroid for every capsule here. And then how we can achieve the equivariance loss here to achieve this extractors, that is transformation equivariance. To do this, we can minimize this loss, equivariance loss here. Basically, we want to align the P here into this pose. Let's see the visualization here. The theta P here correspond to this one. Here. This and this are the same pose, right? And then we apply the inverse of this transformation. Here, we inverse. It means that from this kind of pose, we inverse into this pose, right? This pose is just basically the same here. We do the inverse rotations. And then after we achieve this, we apply this transformation A rotation, so that we will have this kind of pose here. And this pose actually equal to this pose, right? And then basically this loss we will minimize into 0. It means that if we rotate this pose theta P here into the corresponding transformation, inverse transformation P and also transformation A, it will have the same alignment with this capsule A. And if we have the well aligned of these two pose, it will result into 0, right? This one, 0. Okay. So I hope this makes sense to you. And why we minimize this loss? Because we want to encourage that this extractor, this function, to have this property, transformation equivariance property. That is, if we apply the transformations in the input level, or after pass to this extractor, we apply the same transformation, which is this T and TP, the impact are the same. We can still align these two data before and after the extractor. If we can align these two before and after the extractor, it means that the extractor holds transformation equivariance property. And then next we will discuss the descriptor. This is the same. We use the attention metric. And then instead of computing from the point, in this case, for the descriptor, we will compute from the point features here. Point features. And then the output will be just the number of capsule, which is 10 in this case, and embedding dimension, 128 embedding dimension here. And then in this case, we want to enforce the invariance. So the descriptor should be transformation invariance. It's basically just, this is the descriptor of the A from here, from the transformation A, should be the same with the descriptor after we apply the transformation P here. These two descriptors should be the same. Why we ask this property? Because let's say if we have this capsule, head of the airplane, again, no matter the pose of the airplane, the features to describe this head of airplane should be the same. Yeah, I hope this makes sense to you. No matter the transformations, no matter the rotations, no matter the translations, if this capsule belongs to the same part, which is the head in this case, the descriptor should be the same by minimizing this loss. So this is how we can enforce the transformation invariance, this method. And let's discuss next how we achieve the canonicalization. how we achieve a convention of the pose. So canonical pose is just convention. So if we have a random pose like this pose and this pose, we can just decide any pose. It can be this kind of direction, or it can this kind of directions, this kind of directions. Any directions, any pose are okay, as long as all the object consistent, accurate into the same pose. And then to learn this any canonical pose, we will need this K. K in this case is just MLP. And the input is the descriptor here, beta K here. And we will estimate this theta bar here, this. So this is the pose A, this is the pose B, and this is the canonical pose. Again, this is any pose. No need to be this direction, just any pose. And after we estimate this canonical pose, we want compute the transformations that are required to align this into this pose. In this case, we need this kind of rotation, right? Rotate this kind of directions to have the same alignment with this. And in addition, we also compute the needed transformation. So again, here, we rotate this theta from here, and we translate them. We have this result here. And if the distance between this, the alignment distance between this and this should be as minimum as possible, which is close to 0. And to compute these rotations and also the translations, we can use a closed form formula. We do not need to learn anything. For the detail, you can just see this document. Okay, let me delete this first to clean. Okay, so again, this correspond to this, and this theta correspond to this. And then in this case, after we have this canonical pose, we concatenate with the corresponding descriptor here. And we apply this feature. This feature consists of the pose and also the descriptor. We apply to the decoder to reconstruct an original of the shape. And note that the feature that we use is already in the canonical pose. So we expect that the reconstructed input should be also in the canonical pose. This one is canonical feature, and this is the reconstructed shape in the canonical pose here. Okay, and then this is a canonical input. So we apply this PA here. PA is this, and then we use the same transformation that we compute here, because these transformations are those transformations that we need to align this airplane into this canonical pose in the feature space. We can also use the same transformation to align in the input space. Here we use, and because of this extractor, they hold this equivariance property, transformation equivariance property. We can just treat this two are equal, and we simply minimize the chamfer distance, the distance between this and this. For you who are not really familiar with chamfer distance, you can just Google it on the internet. Yeah, so again, I want to emphasize this. We can treat these two equal because we have this equivariance property. It means that we apply the transformation in the feature space after we apply this extractor, or in the input space will result the same. That's basically the transformation equivariance. And then the question is how we can achieve the canonical pose that are consistent across the object. This is the answer. Because the pose, the canonical pose, are estimated from the descriptor, right? The P here. And the descriptors are invariant to any transformation. No matter the pose, no matter the translations we have in the airplane, for example, in the head of airplane, we should have the same descriptor, no matter the pose. And because of we have the same descriptor, we should expect the same output. In this case, is the output is the canonical pose itself. So this way, we can expect that all the point cloud belongs to the same appearance. In this case, is for example, airplane. They will result into the same similar canonical pose. So that's why this paper can achieve this canonical pose, because we already encoded this transformation invariance in our encoder in this method. So that's it. I hope this makes sense to you. If you miss some details, you can try to pause this video and you can comprehend by yourself, or you can directly open the paper and read more details from their papers. And let's see the experimental result. Again, usually people use the well-aligned dataset, like on the airplane, they have this kind of alignment, for example. And if we have a random pose dataset, and the existing method, they try to do the reconstruction from random pose of dataset, it struggles to reconstruct this airplane. And this is the visualization of the result, which is not good. And then this paper, because they already align into a canonical pose, so the corresponding reconstructed airplanes are much better than these two other benchmark method here. So this is in the case of the reconstruction, auto-encoding here. And another use case is they demonstrate in the classifications. They test in the two settings. The first is those dataset that has same alignment. And for those having same alignment, the performance are good. And then for those having no any alignment, so the pose can be just random, we can see that the other method encounter some performance drop here from 90 something to much lower here. And we can see that their method, the canonical pose, they also encounter some drop, but much minimum drop than the other benchmark method here. And here I just show two downstream applications, the reconstructions and also classifications. You can open their papers for any other downstream applications. But the idea is that this paper try to introduce a property that is invariant to affine transformation. Okay, so I think that's it for this video sections, and see you in the next video.